Welcome to another class of intermediate microeconomics. I hope you had a wonderful day today so far, and I hope to help you to have another beautiful 2 hours watching this lecture, although you can also do it in parts. So today's lecture is on game theory and how appropriate we will also derive our real life example from a game that many of us often watch, being soccer. So in soccer, an event that happens now and then is that one of the players needs to kick a penalty. And then the player has to decide whether to kick the penalty left or to the right of the goalkeeper. And this is the action space. So there are two possible actions, kick left or kick right. And the question is, what is the optimal thing for the player to do? Well, most players, they have a preference for left or right because, well, for example, they are right-footed, so they feel that they can kick more precisely the ball into the corner if they aim right. Well, would that be a reason to always kick the ball to the right of the goalkeeper? No, because the goalkeeper will anticipate that. He will know which player he faces and what the preference of the player is. And if the player is known for always kicking the ball to the right, then he will also dive to the right and stop the penalty. So the player will not be successful. So it's not optimal for the player in general to what economists call use a pure strategy, to kick the ball always in the same corner of the net. So to always choose the same action. So it's better for the player, in order not to be fully predictable, to mix between aiming left and aiming right. Now, what we're going to do today is to study that type of games and to arrive at a conclusion to derive what is the optimal mixing between the possible actions. So in this case, the player has two actions. For example, he may prefer to choose to kick the ball to the right because he's right-footed and has more precision, but he cannot always kick to the right, so he will mix. With a certain probability he will kick to the left, with a certain probability to the right. He may kick the ball a little bit more to the right than to the left on average, and we're going to find out, okay, what is then the optimal mixing probability of a player. And this example that is shown here is from a penalty kick in a game between Hamburg and Freiburg a couple of years ago. Actually, the neat thing is that the Dutch player Rafael van der Vaart helps the goalkeeper here by pointing out in which direction the player will kick. And that helped because the goalkeeper dived into this direction and the penalty was stopped. So this is from a real-life game, and economists, they study penalty kicks also professionally. So Palacios Huerta wrote a study on the strategy of kicking penalties, and for that study he analyzed 1,417 penalty kicks that were kicked in the major European leagues, such as the Spanish league, the league in Italy and in England. Now, I think this is a nice advertisement for being interested in doing economic research because, well, doing that type of research will allow you to spend a lot of time watching penalty kicks and to analyze the data. But what did he find? Well, he of these 1,417 penalty kicks, he selected a player that kicked at least 30 penalties. And here you see a number of them listed. So kicker 1 is found to aim left in 32% of the cases and to aim right in 68% of the cases. So he might have a preference for kicking right, but he does not exclusively kick right. And then what Palacios Huerta studies is, okay, how successful is this player when he kicks left and when he kicks right? And it turns out that his scoring rate is identical in both cases. So if he kicks right, he scores 9 out of 10 times. If he kicks left, he also scores 9 out of 10 times. So the payoff of kicking left and kicking right is exactly identical. And this is what we will see in general. If players play a mixed strategy, then the payoff of playing each of the pure strategies is identical in equilibrium. So what he finds is that this penalty kicker follows a Nash equilibrium strategy. When he kicks right, he has more precision there, but it's not as surprising to the goalkeeper. So he scored 9 out of 10 times. If he kicks left, which he does less often, probably he is not as precise to kick the ball into the corner, but there's a surprise effect there because the goalkeeper expects it less that the player will kick left, and he will also score 9 out of 10 times. Now, this not only holds for kicker 1, but the convincing evidence in this study is that if you analyze the different kickers from 1 to 10 as listed here, they mix all with different probabilities. So kicker 5 does an equal mixing between left and right. Kicker 6 has really more often kicks to the right than to the left. But if you look at the scoring rate of the individual players, then you will see that for each of the actions, the scoring rate is almost identical. So you can run a statistical test and you find p-values, and the p-values are quite high. They're never below 5%, meaning that these differences are never statistically significant. So now I hope that you will join me for the rest of the lecture and not start watching soccer saying, okay, this is a nice idea, that's what I should do, watch soccer. Please first continue with the lecture today. Because what we're going to do is we're going to look at games, and we are going to look at different strategies, pure strategies where a player chooses one action with certainty, with probability 1, and mixed strategies where players randomly select from several possible actions, so kicking left or kicking right. And the pure strategies you've already known from previous courses, and the mixed strategies is something that is new to you, or to most of you. So a Nash equilibrium in pure strategies is defined as follows. Suppose that we have a row player and a column player, and the row player's actions are denoted R1 to Rn, and the column player's actions are denoted C1 to Cm. And then we define payoffs. So we know that in the form of utility, so with a U, sometimes it's also denoted with a pi, because that is representing kind of a profit or payoff. And the payoff to player row associated when row plays action Ri and column plays action Cj is given by this functional form over here, which is a function of the actions of both players. So your payoff not only depends on what you do, but also on what the opponent does. And that's what it makes a game. And the same for the column player. Now, usually with 2 players and a limited number of actions, we can represent this game in a matrix form where the payoffs are denoted as entries into the matrix. So this is the famous Battle of the Sexes game. And we have 2 players, a column player and a row player. And the question that they need to decide upon is where to spend the holiday. And these 2 players, they like each other, so they prefer to go on holiday together, but they have their own individual preferences for where to spend the holiday. So the row player is rather in Italy than in Sweden, and the column player prefers Sweden over Italy. So this means that if they end up in Italy, so they both decide to go to Italy, then the row player will get a positive payoff of 2 and the column player a payoff of 1. And if they both decide to go to Sweden, then it's the other way around. The row player gets 1 and the column player gets 2. And in these matrices, always the payoff to the row player is the first entry and the payoff to the column player is the second entry. But then if one of them decides to go to Italy and the other one decides to go to Sweden, then they do not end up together, which is bad for both of them. And in those cases, the payoff of each is equal to 0. So what is the Nash equilibrium in this game? Or what are the Nash equilibria? Now this is something you know as far as we look at pure strategies. So the formal definition of a Nash equilibrium is that it's a pair of strategies such that none of the players has an incentive to deviate from his or her strategy given the strategy of the other players. So formally, the pair of strategies R star, C star is a Nash equilibrium if for both players it holds that the payoff of playing this pair of strategies is at least equal than the payoff if, given what the other player does, one of the players will deviate. So the row player cannot attain a higher payoff if he chooses instead of the equilibrium strategy R star, the action RY, given that the column player plays C star. And the same holds for the column player. Given that the row player plays R star, there's no way that the column player can do better by playing another strategy CJ than C star. So this is the definition of a Nash equilibrium. So no player wants to deviate unilaterally given the choice of the others. And in this case we have so-called pure strategies. So strategies that are played with certainty, with probability 1. So in our game, the Battle of the Sexes game, there are Nash equilibria. And so what are the Nash equilibria of this game? Well, Italy and Sweden are the two Nash equilibria of this game. So you can see it as follows. Given that the column player decides to go to Italy, it's optimal for the row player to choose Italy as well, because in that case he receives a payoff of 2, which is higher than the payoff of 0 when he would go to Sweden. Identically, for the column player, given that the row player decides to go to Italy, we are in this row over here, and you can easily see that in that case, given that the row player chooses Italy, it's optimal for the column player to choose Italy as well, because then the column player's payoff will be 1 instead of 0. And you can also check yourself that Sweden is also a Nash equilibrium in pure strategies of this game. So this you already knew from your previous microeconomics courses. And now we're going to do something that is new. We're going to consider mixed strategies. So like in the example with the penalty kicker, are there additional equilibria where the two players mix between playing Italy and Sweden? Now, in order to find a mixed strategy equilibrium, we first need to define what we look for. So a mixed strategy for a player row is a probability distribution, because now he mixes between the two. And this probability distribution, because we only have two actions, we can represent it by only one number, PR. And PR is the probability with which the row player will play Italy. And then with probability 1 minus PR, he will choose the other action, Sweden. So what the row player now must do, we leave the realm of the pure strategies. So it's no longer between choosing Italy or Sweden with certainty, but the row player has to select PR, the probability with which he will play Italy. So that's the decision variable. And the same for the column player. So the column player must select a probability PC with which the column player will play Italy. Note that this is the same example as in the book, example 8.3, but the notation is slightly different because in the book the notation H and W is used instead of PC and PR, but I prefer the notation that we use here. Okay, so now deriving the Nash equilibria in mixed strategies in this game. And the fundamental idea of the Nash equilibrium remains the same. So if a pair of strategies is equilibrium strategy in mixed strategies, then it must hold that the choice of each of the player is optimal given what the other player does. So for the row player, his choice of PR must be optimal given that the column player chooses PC, and for the column player, choosing PC must be optimal to her given that the row player chooses PR. And note that here we assume that each player holds correct beliefs about the opponent's behavior. So we impose a rational expectations assumption in order to close the model. So if the row player decides to play Italy with probability PR, then we assume that the column player has the correct belief that the row player will choose Italy with probability PR.